The Moon sits about 384,000 kilometers from Earth. We reached it in 1969 with computers less powerful than a modern phone. Mars, at its closest approach, is around 55 million kilometers away. That's roughly 143 times the distance to the Moon. If we manage the Moon with 1960s technology, Mars with today's capabilities should be straightforward math. More distance, yes, but we've had 50 additional years of advancement. The assumption feels reasonable. It's also the beginning of a significant misunderstanding about what makes reaching Mars genuinely difficult. If you find this kind of breakdown useful, interacting with the video helps the platform know to recommend similar explanations to you later, so there's that option if you're interested. The International Space Station orbits Earth every 90 minutes. Astronauts have lived there continuously since November 2000. We've learned how to keep humans alive in space for months at a time. We resupply the station regularly. We return crew members safely. The systems work. They've worked for over 2 decades. Space habitation is a solved problem in practical terms. We know how to do it. That knowledge should transfer to a Mars mission. The duration would be longer, certainly, but the principles remain the same. Keep the pressure stable, recycle the air, manage the water, provide food, maintain temperature. We've done this for years. So why hasn't anyone gone to Mars yet? The answer people usually give is distance. Mars is far away. That's true. But distance alone doesn't explain why we haven't gone. Distance is a number. Numbers can be managed with fuel and time. There's something else that makes Mars missions fundamentally different from everything we've done in space so far. Consider what happened with Apollo 13. An oxygen tank exploded. The mission had to abort. The crew used the lunar module as a lifeboat. They looped around the Moon and came home. The entire emergency lasted less than 6 days from explosion to splashdown. Ground control worked continuously. Engineers ran simulations. Solutions were developed, tested, and transmitted. The crew implemented them. Everyone survived because the Earth was close enough for real-time communication, and close enough that the return trajectory took only days. Now imagine the same failure happening on the way to Mars. The communication delay alone would be between 4 and 24 minutes one way, depending on where Earth and Mars are in their orbits. A conversation that takes 30 seconds on Earth would take up to an hour round trip at Mars distances. By the time ground control hears about a problem, discusses it, and sends a solution, the crew might have run out of options. But even that communication delay isn't the real constraint. The real constraint is that you can't turn around. When the Apollo 13 oxygen tank exploded, they were about 320,000 kilometers from Earth. They could abort and be home in 4 days. If the same explosion happened 3 months into a Mars mission, when you're perhaps 100 million kilometers from Earth and 150 million kilometers from Mars, you can't come home quickly. The fuel requirements to reverse course and return to Earth would be astronomical, likely exceeding what any realistic spacecraft could carry. You'd need to accelerate back toward Earth, which requires burning fuel equal to the amount you already burned getting that far. Then you'd need to slow down when you reached Earth. The mass penalties make it impossible with current propulsion. The only realistic option is to continue to Mars, even if systems are failing. This irreversibility is not a characteristic of lunar missions or space station operations. Every previous human spaceflight could abort to Earth within days or, in the case of the ISS, within hours. Mars missions cannot. Once you pass a certain point, you're committed to completing the entire mission regardless of what happens. That changes everything. The typical Mars mission profile looks like this. You launch from Earth during a specific window that opens roughly every 26 months when Earth and Mars are properly aligned. This alignment is necessary because you're not flying straight to Mars. You're launching from a planet moving at 30 kilometers per second in one direction, trying to reach a planet moving at 24 kilometers per second in a different direction. You need to enter an elliptical transfer orbit that intersects Mars's orbit at the exact moment Mars arrives at that point. The most fuel-efficient trajectory is called a Hohmann transfer orbit. It takes about 9 months. Some faster trajectories exist that take 6 or 7 months, but they require significantly more fuel. Once you reach Mars, you need to slow down enough to enter orbit or land, which also requires fuel. Then, if you want to come back, you need to wait on Mars until Earth and Mars align again for the return journey. That wait is typically another 9 to 16 months. Then you take another 6 to 9 month journey back. The total mission duration is somewhere between 2 and 3 years. That's not speculative. That's orbital mechanics. The planets move in fixed paths at fixed speeds. You can't change that. So here's where the earlier assumption breaks down. Keeping astronauts alive on the space station for 6 months proves we can maintain life support for 6 months with regular resupply from Earth, which is 3 days away. A Mars mission requires keeping astronauts alive for 2 to 3 years with no possibility of resupply and no possibility of evacuation. The difference isn't just duration. It's compounding reliability over time under irreversible conditions. Every system that works on the ISS must work perfectly for 4 to 6 times longer on a Mars mission, with zero external support. If a water recycling system fails on the ISS, a replacement is sent up on the next cargo flight within weeks. If it fails on the way to Mars, the crew must repair it with only the spare parts they brought, or they will run out of water before reaching Mars. There is no resupply. There is no rescue. The mission is entirely self-contained for years. The amount of consumables required becomes staggering when you extend the timeline. An astronaut on the ISS needs about 30 kilograms of supplies per day when you account for food, water, and oxygen, even with recycling systems. For a crew of 6 on a 3-year mission, that's about 197 tons of supplies if nothing is recycled. Obviously, recycling is essential. Current ISS life support systems recycle about 90% of water and 42% of oxygen. That brings the supply requirement down, but not enough. Even with advanced recycling, you're still looking at dozens of tons of consumables for the crew alone. Then there's the spacecraft structure, the propulsion systems, the fuel, the power systems, the scientific equipment, the Mars lander if you're actually landing, the ascent vehicle to get back off Mars, and redundant backups for every critical system because there's no way to get replacements. The total mass of a realistic Mars mission spacecraft is estimated to be somewhere between 500 and 1,000 tons in low Earth orbit, depending on mission architecture. For reference, the ISS weighs about 420 tons, and it was assembled over 10 years with 42 separate launches. Getting 500 tons to Mars, with most of that being fuel, is an enormous challenge. Here's another layer. Fuel isn't just fuel. The propulsion system has to carry the fuel to burn the fuel. Rocket engines operate on the principle that for every kilogram of spacecraft mass, you need multiple kilograms of propellant to change its velocity by a given amount. This relationship is described by the Tsiolkovsky rocket equation. To increase your velocity by 1 km per second, a typical chemical rocket with a specific impulse of 450 seconds needs about 2.4 kilograms of propellant for every kilogram of final spacecraft mass. A Mars mission requires a total velocity change of roughly 9 to 13 kilometers per second, depending on the trajectory and whether you're using aerobraking. If your spacecraft has a dry mass of 100 tons, the propellant mass required could easily exceed 400 tons. But the propellant itself has mass, so you need fuel to carry the fuel. The mass grows exponentially. This is why the mass estimates for Mars missions are so high. You're not just carrying the spacecraft. You're carrying the fuel to move the spacecraft, the fuel to move that fuel, and the fuel to move that fuel. The tyranny of the rocket equation makes every kilogram expensive. Some mission plans involve sending fuel to Mars ahead of time, producing fuel on Mars using local resources, or using nuclear propulsion to improve efficiency. These strategies reduce the mass problem but introduce other complexities. In situ resource utilization, where you make fuel on Mars from the atmosphere, sounds efficient, but it requires landing a fuel production facility on Mars, ensuring it works remotely for months or years before the crew arrives, and confirming you've actually produced enough fuel before committing the crew to launch. If the fuel production fails, the crew would be stranded on Mars with no way to return. Nuclear propulsion offers better efficiency than chemical rockets, but it requires developing, testing, and rating a nuclear engine for human spaceflight, which hasn't been done yet. Every solution to one problem creates another problem that must also be solved. Now consider radiation. In low Earth orbit, astronauts are partially protected by Earth's magnetic field. The field deflects much of the charged particle radiation from the Sun and cosmic rays from deep space. Mars has no global magnetic field. It lost its magnetic field billions of years ago. The trip to Mars and the time spent on Mars expose astronauts to significantly higher radiation doses than any humans have experienced. Galactic cosmic rays are high-energy particles, mostly protons and helium nuclei, traveling near the speed of light. They pass through spacecraft walls, through spacesuits, through human tissue. When they pass through cells, they damage DNA. Some of that damage is repaired by cellular mechanisms. Some of it isn't. Cumulative radiation exposure increases cancer risk and can cause acute radiation sickness at high doses. Solar particle events, which are bursts of radiation from solar flares, can deliver dangerous doses in hours. Shielding helps, but only to a point. Thick shielding stops more radiation but adds mass, which requires more fuel, which adds more mass. The optimal balance between protection and mass is still being determined. Current estimates suggest a round-trip Mars mission would expose astronauts to around 1 sievert of radiation, possibly more depending on solar activity. For reference, the annual dose limit for radiation workers on Earth is 50 millisieverts. A full-body CT scan is about 10 millisieverts. 1 sievert increases lifetime cancer risk by roughly 5%. That's not immediately lethal, but it's significant. The radiation exposure on a Mars mission would exceed NASA's current career limits for astronauts, which are designed to keep lifetime cancer risk increases below 3%. Those limits would need to be revised or waived for Mars missions. There's no way to eliminate the radiation risk with current technology. You can reduce it with shielding, with faster transit times using more powerful propulsion, or with pharmaceutical countermeasures that are still under development, but you can't remove it. Astronauts going to Mars would accept a level of risk higher than any previous spaceflight. Then there's the psychological component. Isolation and confinement studies on Earth have shown that small groups in isolated environments for long periods experience predictable stresses. Communication delays mean conversations with family, friends, or mission control feel disconnected. The Earth becomes a small blue dot, then eventually invisible to the naked eye as you travel farther away. The crew would be more isolated than any humans in history, by distance and by communication delay. Analog studies, such as the Mars 500 simulation where a crew spent 520 days in a sealed facility in Moscow, provide some data on how people cope, but those studies had the implicit safety net that participants could leave in an emergency. A real Mars crew would not. The knowledge that there is no escape, no rescue, and no quick return if something goes wrong adds a psychological weight that simulations can't fully replicate. Cognitive performance can decline under chronic stress. Sleep disturbances are common in confined environments and in microgravity. Interpersonal conflicts in small groups become more significant when there's no escape. One astronaut having a psychological crisis could endanger the entire mission if their role is critical. Crew selection and training for Mars missions would need to account for psychological resilience in ways that current astronaut selection doesn't fully address, because current missions always have the option of returning to Earth relatively quickly. Mars missions don't. The psychological readiness required is different in kind, not just degree. Let's return to the idea of mission duration and system reliability. Spacecraft systems are designed with expected lifetimes. Electronic components degrade over time. Seals dry out. Materials fatigue. Moving parts wear. Radiation damages electronics. On the ISS, components are replaced regularly. Entire modules have been swapped out. Maintenance is continuous. A Mars spacecraft would need to function for 2 to 3 years with only the maintenance the crew can perform using onboard tools and spare parts. Every critical system needs redundancy, and the redundant systems need to be reliable for the full mission duration. The probability of a critical failure increases with time. If a system has a 1% chance of failing in any given year, the probability that it survives 3 years is about 97%. That sounds acceptable until you realize a spacecraft has hundreds of critical systems. If each has a 1% annual failure rate, the probability that all of them survive 3 years is much lower. You can add redundancy, which helps, but redundancy adds mass and complexity. More components mean more potential failure modes. Balancing reliability, redundancy, and mass is a design challenge without a perfect solution. Landing on Mars introduces another set of difficulties. Mars has an atmosphere, but it's thin, only about 1% of Earth's atmospheric pressure at the surface. That's thick enough to create significant heating during entry, requiring heat shields, but too thin for parachutes alone to slow a spacecraft to a safe landing speed. Mars landers use a combination of heat shields, parachutes, and retro rockets. For small robotic landers like Curiosity, which weighed about a ton, this works. For a human-rated lander carrying crew, habitats, supplies, and an ascent vehicle, the mass could be 40 or 50 tons or more. Slowing that much mass in Mars's thin atmosphere requires more advanced techniques. NASA's proposed solutions include supersonic retropropulsion, where rockets fire while the spacecraft is still moving faster than the speed of sound through the thin atmosphere, and inflatable heat shields. These technologies are under development, but haven't been tested at the scale needed for human missions. The landing precision also matters. You need to land near your pre-deployed supplies and ascent vehicle, within perhaps a few kilometers. Mars has unpredictable dust storms, high surface winds during certain seasons, and varied terrain. Achieving pinpoint landings with heavy payloads in those conditions is not yet a demonstrated capability. Assuming you land successfully, the surface stay introduces more complications. Mars's surface temperature averages around -63 degrees Celsius, with variations from -125 at the poles to about 20 degrees near the equator during summer. Any habitat needs heating. Dust storms can last for weeks or months and can cover the entire planet, reducing sunlight and covering solar panels. A major dust storm in 2018 caused the Opportunity rover to lose power and eventually cease functioning. A crew on Mars would need power systems that can operate through extended dust storms, which likely means nuclear power rather than solar. Radiation exposure on the surface is lower than in space because the planet itself provides some shielding, but it's still significantly higher than on Earth. The crew would need to minimize time outside and possibly pile Martian soil over parts of their habitat for additional shielding. Martian dust is also a hazard. It's fine, abrasive, and possibly toxic. It sticks to everything due to static charge. It can damage seals, contaminate airlocks, and potentially harm lungs if inhaled. Managing dust contamination is a significant engineering problem. The ascent vehicle presents its own challenge. To leave Mars and return to Earth, the crew needs a rocket capable of launching from the Martian surface, reaching orbit, and then performing the trans-Earth injection burn. If that rocket was brought from Earth, it needs to survive sitting on Mars for a year or more, exposed to dust, temperature extremes, and radiation, and then function perfectly when needed. If the fuel is produced on Mars, the production equipment needs to work reliably without human intervention for months before the crew even arrives. Either way, the ascent vehicle is a single-point failure. If it doesn't work, the crew cannot leave Mars. There is no backup. Building in redundancy by bringing two complete ascent vehicles doubles the mass that must be landed on Mars. The trade-offs are difficult. The ascent vehicle presents its own challenge. To leave Mars and return to Earth, the crew needs a rocket capable of launching from the Martian surface, reaching orbit, and then performing the trans-Earth injection burn. If that rocket was brought from Earth, it needs to survive sitting on Mars for a year or more, exposed to dust, temperature extremes, and radiation, and then function perfectly when needed. If the fuel is produced on Mars, the production equipment needs to work reliably without human intervention for months before the crew even arrives. Either way, the ascent vehicle is a single-point failure. If it doesn't work, the crew cannot leave Mars. There is no backup. Building in redundancy by bringing two complete ascent vehicles doubles the mass that must be landed on Mars. The trade-offs are difficult. Let's examine one more assumption. We tend to think of Mars missions as analogous to early exploration on Earth, like the voyages of Cook or Magellan, dangerous but undertaken with the technology of their time. That analogy is misleading. Those explorers traveled through environments where humans can survive. They breathed the air. They could find or carry food and water. If their ships sank, they might reach land and survive. Mars offers none of that. The atmosphere is unbreathable. The pressure is too low to sustain liquid water in human tissues. The temperature would cause rapid hypothermia. There is no food. There is no drinkable water accessible without significant processing. Every breath, every drink, every degree of warmth, every bit of pressure keeping your blood liquid, depends on functioning technology. A single breach in a spacesuit on Mars would be fatal within seconds. Unconsciousness from hypoxia would occur in about 15 seconds. Death would follow shortly after. There is no partial failure mode where you survive in a degraded state. It's binary. The technology works or you die. That's not exploration as we've historically understood it. It's more like visiting the ocean floor in a submarine. The environment is absolutely hostile. Survival is entirely dependent on a sealed vessel with functioning life support. The difference is that submarines can surface in hours and rescue is possible within days. Mars missions cannot surface, and rescue is impossible. Another point worth considering is medical care. On the ISS, if an astronaut has a medical emergency, they can be back on Earth within hours using a Soyuz or Crew Dragon capsule. On a Mars mission, the crew will include someone with medical training, likely a physician, but the available equipment and supplies will be limited by mass constraints. Surgery in microgravity is difficult. Blood doesn't flow downward. It floats. Anesthesia management is more complicated without gravity. Infection control in a closed environment where everything is recycled is challenging. If an astronaut develops appendicitis on the way to Mars, the only option is for the onboard physician to perform an appendectomy using the available supplies, in microgravity, with no possibility of evacuation if complications arise. Medical scenarios that would be routine emergencies on Earth become life-threatening on a Mars mission. The crew would need training for medical situations well beyond what current astronauts receive, and the spacecraft would need to carry a much more extensive medical kit than current missions. That adds mass, training time, and complexity. Microgravity itself is another chronic exposure. Astronauts on the ISS experience bone density loss at a rate of about 1 to 2% per month, despite daily exercise. Muscle atrophy occurs similarly. Vision problems caused by fluid shifts toward the head affect many astronauts, and can be permanent. A Mars mission involves 6 to 9 months of microgravity each way. By the time astronauts reach Mars, they would have experienced significant bone and muscle loss. Mars's gravity is only 38% of Earth's, which is better than microgravity but still low enough that it might not prevent continued atrophy. When the crew attempts to land on Mars, they would need to be physically capable of handling emergency situations in a weak and potentially disoriented state. Current exercise countermeasures on the ISS require about 2 hours per day per astronaut. That's time not spent on mission tasks, and the exercise equipment adds mass. More intensive countermeasures might be needed for Mars missions, which means more equipment, more mass, more time spent exercising instead of working. There's no free solution. Microgravity exposure is harmful, countermeasures are only partially effective, and both the harm and the countermeasures cost resources. Water recycling is worth looking at more closely. The ISS recycles about 90% of water, which sounds excellent until you calculate what happens with the remaining 10% over 3 years. If each astronaut uses 50 liters of water per day, and 10% is lost, that's 5 liters per astronaut per day that must be replaced. For 6 crew members over 3 years, that's about 33,000 liters of water that must be carried as reserve, which is 33 tons. Improving recycling efficiency to 95% cuts that in half, to 16.5 tons. Every percentage point of improvement saves significant mass. But achieving higher recycling efficiency requires more complex systems, which are heavier, use more power, and have more potential failure modes. The ISS system works at 90% because it's been continuously refined over 2 decades with the ability to replace parts and adjust procedures. A Mars mission would need to achieve similar or better efficiency from the start, with no opportunity for iterative improvement during the mission. The system must work correctly for 3 years with minimal maintenance. That's a much harder requirement. Air recycling has similar constraints. The ISS generates oxygen by electrolyzing water, which splits water into hydrogen and oxygen. The oxygen is released into the cabin. The hydrogen is either vented or combined with carbon dioxide in a Sabatier reactor to produce water and methane. The methane is vented. This system recovers some of the oxygen that would otherwise be lost as carbon dioxide, but not all of it. A Mars mission would benefit from a closed-loop system where nothing is vented, but achieving that requires additional processing steps, more equipment, more mass, more power, and more complexity. Each added component is another potential failure point. The balance between system closure and system reliability is another design trait that doesn't have an obvious answer. Power generation is another constraint. The ISS uses solar panels and operates in an orbit where sunlight is available most of the time. The panels degrade over time due to radiation and micrometeorite impacts, but they can be replaced. A Mars spacecraft traveling through interplanetary space would receive decreasing sunlight as it moves away from the Sun, reaching about half the intensity at Mars compared to Earth orbit. Solar panels would need to be larger to provide the same power, or the spacecraft would need to use less power, or an alternative power source would be necessary. Nuclear power, specifically a radioisotope thermoelectric generator or a fission reactor, provides consistent power regardless of distance from the Sun and works during dust storms on Mars, but it adds mass, regulatory complexity, and safety considerations. Launching nuclear material requires additional safety measures in case of a launch failure. Operating a fission reactor in space requires cooling systems and shielding. There are trade-offs in every direction. Communication is another subtle constraint. The communication delay between Earth and Mars varies from about 4 minutes one way when the planets are closest to 24 minutes one way when they're on opposite sides of the Sun. During solar conjunction, when Mars is directly behind the Sun from Earth's perspective, communication can be blocked entirely for a few weeks. The crew would need to operate autonomously during that period. Even during normal communication windows, the delay means the crew cannot rely on real-time advice from mission control for time-critical decisions. If something goes wrong, the crew must diagnose and respond immediately. Ground control can provide analysis and suggestions, but only after a delay that might be too long. This autonomy requirement means the crew needs broader and deeper training than current astronauts. They need to understand their spacecraft systems at an engineering level, not just an operational level. They need medical training beyond basic first aid. They need the ability to improvise repairs with available materials. The skill set required is more similar to Antarctic winter-over crews or submarine crews than current astronauts, with the added complication that there's no possibility of outside help. The psychological impact of the communication delay is also worth considering. Conversations with loved ones become asynchronous exchanges rather than real-time dialogue. You send a message and wait 10 to 50 minutes for a response. That delay disrupts the natural flow of conversation and makes emotional support more difficult to provide and receive. Astronauts have reported that real-time communication with family is one of the most important factors in maintaining morale during long-duration missions. Mars crews would lose that. Video messages replace conversations. The emotional isolation could be significant for some crew members. Psychological support would need to be largely peer-based within the crew, with delayed support from Earth as a secondary resource. Crew dynamics become even more critical when the crew is the primary source of social and emotional support for each other. A conflict that would be a minor inconvenience on the ISS could become a mission-threatening problem on a Mars mission. Let's consider mission abort scenarios more carefully. On the ISS, if a critical system fails, the crew can evacuate immediately using docked spacecraft. On a Mars mission, there is no evacuation. If the spacecraft suffers a critical failure during the coast phase to Mars, the crew has limited options. They can attempt repairs using available resources. If repairs aren't possible, they would continue coasting toward Mars, hoping to arrive alive, or they might attempt to alter course to return to Earth, which would extend the mission duration and require fuel that might not be available. If the failure is life support related and cannot be fixed, the crew would die before reaching either planet. There's no good abort option once you're committed to the trajectory. Mission planning would need to account for scenarios where the crew must continue despite failures, rationing consumables, cannibalizing non-essential systems for parts, and improvising solutions. The ability to continue a mission in a degraded state is a requirement, not an option. That level of resilience must be designed into the spacecraft from the beginning, which adds mass and complexity. Entry, descent, and landing on Mars, often called the 7 minutes of terror for robotic missions, would be even more intense for a crewed mission. The entry velocity is around 6 kilometers per second. The spacecraft must slow to zero at the surface without exceeding acceleration limits that humans can survive, without landing in a hazardous location, and without depleting fuel reserves. The entire sequence is automated because the communication delay prevents real-time control from Earth. The crew can monitor but not intervene in most scenarios. If the automated system fails, there might not be time for manual override. The landing must work correctly the first time. There's no second attempt. Mission designers would need extraordinarily high confidence in the landing system before committing a crew to use it. That confidence comes from extensive testing, but testing a large-scale Mars landing system on Earth is difficult because Earth's atmosphere is much thicker than Mars's. Testing on Mars is possible but expensive and time-consuming. You need multiple successful robotic landing demonstrations at the scale and mass needed for crewed missions before attempting a crewed landing. That's years of preliminary missions and significant costs before the first crew even launches. The return journey from Mars to Earth introduces yet another set of risks. After spending a year or more on Mars, the crew must launch into Mars orbit, rendezvous with the return spacecraft if it's a separate vehicle, or prepare their ascent vehicle for the trans-Earth injection burn. The ascent from Mars must be successful on the first try because there's no second vehicle. Then comes another 6 to 9 months in microgravity, further degrading bone and muscle. By the time they approach Earth, the crew would have been in space or on Mars for 2 to 3 years. Their physical condition would be worse than any previous astronauts. The final challenge is Earth re-entry. Returning from Mars, the spacecraft is traveling at around 11 kilometers per second relative to Earth, faster than any crewed spacecraft has traveled before. The Apollo capsules return from the Moon at about 11 kilometers per second, which is the edge of current experience. A Mars return might be slightly faster depending on the trajectory. The heat shield must protect the crew during re-entry, and the landing must be accurate. If the crew survives everything else, a failure during Earth re-entry or landing would be a bitter end. Redundancy in landing systems is essential, but again, redundancy means mass. The total cost of a Mars mission is another constraint, though it's not a physical constraint like mass or energy. Estimates for the first crewed Mars mission range from $100 billion to several $100 billion spread over 10 to 20 years. For comparison, the Apollo program cost about $280 billion in today's dollars. The ISS has cost over $150 billion over its lifetime. Mars missions would likely be more expensive than either because they require new hardware, extensive testing, and multiple preliminary missions. Government space budgets are limited. Sustained funding over decades is difficult to secure politically, especially for a program with no immediate economic return. Funding uncertainty delays development and increases costs because programs that start and stop repeatedly waste resources. Private funding is possible, but private entities need a return on investment. The return on investment for Mars exploration is not clear in economic terms. Scientific knowledge and national prestige have motivated past space programs, but those motivations fluctuate with political priorities. The economic constraint is not insurmountable, but it's real and has historically been the limiting factor for ambitious space programs. There's also the question of mission architecture decisions that have cascading effects. Do you send the crew in one spacecraft or split them between multiple spacecraft for redundancy? One spacecraft is simpler but creates a single point of failure. Multiple spacecraft increase complexity, require more launches, and need coordination, but provide redundancy. Do you send cargo missions ahead of the crew to preposition supplies on Mars, or do you send everything together? Prepositioning is more efficient but requires trusting that the cargo arrives safely and is functional when the crew arrives months or years later. Sending everything together means the crew has immediate access to supplies but increases the mass that must travel with the crew, which increases fuel requirements. Do you plan for a surface stay of 30 days or 500 days? Longer stays allow more science but require more supplies, more robust habitats, and mean the crew spends more time exposed to Mars radiation. Shorter stays reduce those risks but limit what can be accomplished, and require waiting in Mars orbit or on the surface for the return window, which also requires supplies and exposure. Every choice has implications for mass, cost, risk, and mission objectives. There's no universally optimal architecture. Different mission plans make different trade-offs based on different priorities. One approach to reducing mass is in situ resource utilization, producing fuel, water, and oxygen on Mars using local resources. Mars's atmosphere is 95% carbon dioxide. The Sabatier reaction can convert carbon dioxide and hydrogen into methane and water. Electrolysis can split water into hydrogen and oxygen. Methane and oxygen can fuel rockets. If you bring hydrogen from Earth and extract carbon dioxide from Mars's atmosphere, you can produce methane fuel and oxygen oxidizer on Mars. This dramatically reduces the mass you need to carry from Earth because you're only bringing the hydrogen and the equipment, not the full fuel load for the return journey. The concept is sound. NASA's MOXIE experiment on the Perseverance rover has successfully produced small amounts of oxygen from Mars's atmosphere. Scaling that up to produce tons of fuel for a crewed mission is the challenge. The equipment would need to be landed on Mars, activated remotely, and operated for months to fill fuel tanks. It would need to work without human intervention, in Mars's environment, with dust storms, temperature variations, and equipment wear. If it fails, the crew's return is in jeopardy. You would want to verify fuel production is complete and successful before launching the crew from Earth, which means the fuel production mission would need to arrive at Mars a year or more before the crew. That extends the total program timeline and adds complexity, but it's likely necessary to make Mars missions feasible with current propulsion technology. Another technology that could help is nuclear propulsion. Nuclear thermal rockets heat propellant using a nuclear reactor instead of chemical combustion. They can achieve roughly twice the efficiency of chemical rockets, which reduces the propellant mass needed. A Mars mission using nuclear propulsion could have shorter transit times, reducing crew radiation exposure and life support demands. Alternatively, nuclear electric propulsion uses a reactor to generate electricity, which powers ion thrusters. Ion thrusters are extremely efficient but produce low thrust, so acceleration is gradual. Transit times might actually be longer, but the fuel efficiency allows for more payload mass. Both nuclear propulsion types have been studied extensively, and some ground testing has been done, but neither has flown in space with humans. Developing, testing, and certifying nuclear propulsion for crewed missions would take years and significant funding. The political and regulatory hurdles for launching nuclear reactors are also substantial. Nuclear propulsion is not a near-term solution, but could enable Mars missions in the longer term. Some proposals suggest using Mars's moons, Phobos and Deimos, as staging points. Phobos orbits very close to Mars, only about 6,000 kilometers above the surface. Its gravity is negligible, so landing and launching requires minimal fuel. A mission could establish a base on Phobos, use it to store supplies, and ferry crew and cargo between Phobos and Mars's surface using smaller vehicles. This approach breaks the mission into smaller, more manageable steps and provides a safe haven close to Mars. The challenges are that it requires multiple vehicles and missions to set up, adds complexity, and Phobos itself is a harsh environment with no atmosphere and no protection from radiation. It's an interesting idea but not simpler than a direct Mars landing. It trades one set of challenges for another. Public and political support for Mars missions is another factor. The Apollo program succeeded partly because it had a clear geopolitical motivation during the Cold War. Mars missions don't have that same urgency. Public interest in space exploration varies. After Apollo 11, public attention to subsequent moon landings dropped significantly. A Mars mission would generate enormous interest initially, but sustaining that interest through a 2 or 3 year mission, and sustaining political support through 10 to 20 years of preparation, is uncertain. If public or political support wanes during the mission, it could affect funding for follow-up missions or even support for bringing the crew home if unexpected costs arise. The first Mars mission would need to be successful and remain publicly engaging throughout to secure support for future missions. That's a non-technical constraint but an important one. Crew selection for a Mars mission would be unlike any previous astronaut selection. Current astronauts are selected for technical skills, physical fitness, and psychological stability for missions lasting 6 months with the option to return early if needed. Mars crew would need those qualities plus resilience from multi-year isolation, ability to work effectively in a small team with no outside support, medical skills to handle emergencies, engineering skills to improvise repairs, and psychological stability under the knowledge that there is no escape and no quick rescue. The selection pool might be smaller than for current missions because the requirements are more stringent. Training would also be longer and more intensive. The crew would need to train together for years to develop the cohesion and trust necessary for such a mission. That training period is itself a significant commitment for the individuals involved. Let's also consider what happens if something goes wrong catastrophically. If a Mars mission fails and the crew dies, it would be a highly public tragedy affecting international space programs for years, similar to how the Challenger and Columbia disasters affected the Space Shuttle program. The political and public reaction could halt Mars exploration for a decade or more. The consequences of failure are not just the loss of the crew but potentially the end of crewed Mars exploration for a generation. That raises the bar for acceptable risk. How much risk is acceptable for a Mars mission? There's no objective answer. Different cultures and space agencies have different risk tolerances. NASA's risk assessment for Mars missions would need to balance the goal of exploration against the probability of crew loss and the consequences of that loss. That's ultimately a values question as much as a technical one. Given all these constraints, why hasn't anyone gone to Mars yet? It's not primarily because Mars is far away, though distance contributes. It's because the combination of distance, duration, isolation, irreversibility, mass requirements, radiation exposure, system reliability demands, and the need for near-perfect execution over years exceeds our current capabilities and risk tolerance. We can reach Mars with robotic probes because robots don't need life support, don't experience psychological stress, don't require return trips, and can accept failure rates that would be unacceptable for crewed missions. Losing a robotic probe is disappointing and expensive. Losing a crew is a tragedy that affects entire programs. The acceptable failure rate is orders of magnitude different. The fundamental insight is that Mars missions are not just longer lunar missions. They're qualitatively different. Lunar missions could abort to Earth within days. Mars missions cannot abort. Lunar missions were supplied from Earth every few months. Mars missions must be entirely self-sufficient for years. Lunar astronauts were 3 days from home. Mars astronauts would be 3 to 9 months from home, depending on when the emergency occurs and where the planets are in their orbits. The support infrastructure that makes space station operations routine, resupply missions, crew rotation, emergency evacuation, real-time communication, continuous ground support, doesn't exist for Mars. It can exist for Mars given the distances and orbital mechanics involved. Mars missions must succeed without that infrastructure. That's a fundamentally different problem. Consider also the testing challenge. We test spacecraft systems extensively before committing crews to use them. But how do you test a Mars mission without actually going to Mars? You can test components on Earth. You can test some systems on the ISS. You can send robotic precursor missions. But a full-scale test of a crewed Mars mission architecture, with all systems operating together for 3 years under mission conditions, would effectively be the mission itself. There's no way to replicate Mars mission conditions fully without going to Mars. That means the first crewed mission would be operating systems that have never been tested as a complete integrated system under real mission conditions. Some level of uncertainty is unavoidable. The engineers and planners would need extremely high confidence in their models, simulations, and component tests, knowing that full system testing isn't possible. That confidence takes time to build and requires rigorous engineering processes. Another consideration is crew health monitoring and medical research. We don't have long-term data on human health during 3-year space missions. The longest single space flight was 437 days by Valery Polyakov on Mir. Most ISS missions are 6 months. A Mars mission would be 4 to 6 times longer. Some health effects might not appear until after 6 months or a year. Bone density loss continues throughout microgravity exposure. Vision problems caused by intracranial pressure changes can worsen over time. Radiation damage accumulates. Psychological stress can build gradually. We would be sending crew into a duration of space exposure beyond our current medical knowledge. Medical monitoring during the mission is essential, but if health problems emerge during the mission, treatment options are limited. Bringing crew home early isn't possible. Medical evacuation doesn't exist. The crew's health must be maintained with onboard resources for the full mission duration, regardless of what health issues develop. Extensive pre-mission medical screening can reduce risks but can't eliminate them. The question of mission success criteria is also important. What defines a successful Mars mission? Arriving at Mars? Landing safely? Conducting science? Returning safely? All of the above? Different stakeholders might have different definitions. Scientists want research conducted. Engineers want systems validated. The public wants astronauts to return safely. Sponsors want their objectives met. If the mission reaches Mars but cannot return, is that success or failure? If the crew returns but scientific objectives aren't met, is that success? These questions need clear answers before the mission begins because they affect design decisions. A mission designed primarily to return crews safely might make different trade-offs than a mission designed primarily to maximize science return. The priorities shape the architecture. There's also the matter of international cooperation versus national programs. The ISS is a highly successful international collaboration. A Mars mission could follow that model, sharing costs, expertise, and risks among multiple nations. International cooperation spreads the financial burden and pools technical capabilities. It also introduces coordination challenges, political complexities, and dependencies on partner nations maintaining their commitments over decades. Alternatively, a single nation or entity could pursue Mars independently, maintaining full control but bearing full cost and risk. There are advantages and disadvantages to both approaches. The political landscape will likely determine which path is taken, and that political landscape can change over the years required to develop and execute a Mars mission. One specific technical challenge worth examining further is the Mars entry, descent, and landing mass problem. The largest payload successfully landed on Mars is the Perseverance rover at about 1 ton. A crewed mission would need to land something like 40 to 60 tons, possibly more. That's 40 to 60 times heavier. The techniques that work for 1-ton payloads might not scale linearly. Atmospheric drag, heat shield mass, parachute size, and rocket thrust all scale in complex ways with mass. Very large heat shields are difficult to package inside rocket fairings. Very large parachutes have deployment challenges. Supersonic retropropulsion, where rockets fire while the vehicle is still traveling faster than sound through the atmosphere, is one proposed solution. NASA tested this with Falcon 9 booster landings, which demonstrated supersonic retropropulsion in Earth's atmosphere. Mars's thinner atmosphere presents different challenges. The concept seems feasible but needs validation at Mars. That validation probably requires landing increasingly heavy robotic payloads on Mars to test the techniques before committing a crew. Each test mission takes years to develop and costs hundreds of millions to billions of dollars. The development timeline for proven large-scale Mars landing capability is measured in decades, not years. Dust mitigation is another unglamorous but critical challenge. Martian dust is electrostatically charged and clings to surfaces. It's fine enough to work into seals and mechanisms. It's abrasive enough to damage equipment over time. The Apollo astronauts brought lunar dust into their spacecraft after moonwalks, and it caused problems despite their best efforts to brush it off. Lunar dust and Martian dust have different properties, but both are difficult to manage. A Mars habitat would need airlocks designed to minimize dust intrusion. Spacesuits would need to be maintained carefully to prevent dust from degrading seals. Equipment exposed to Martian environment would need protection from dust accumulation. Dust storms can reduce visibility and cover solar panels, as mentioned earlier. Dust is a pervasive problem without a complete solution. It can be managed with good design, but it cannot be eliminated. Long-term equipment reliability on Mars requires accounting for dust exposure. Another biological consideration is the adaptation to Mars gravity after months in microgravity. When astronauts return to Earth from the ISS, they experience difficulty walking and standing initially because their bodies adapted to microgravity. Balance is impaired. Muscles are weakened. Blood pressure regulation is affected. It takes days to weeks to readapt to Earth gravity. Mars astronauts would arrive at Mars after 6 to 9 months in microgravity. Their bodies would be similarly adapted to microgravity. Mars gravity is 38% of Earth's, stronger than microgravity but much weaker than Earth. It's unclear how quickly astronauts would adapt to Mars gravity, or whether Mars gravity would be sufficient to restore normal function. They might remain weakened and disoriented for some time after landing. If an emergency occurs during landing or shortly after, the crew might not be physically capable of responding effectively. This risk can be mitigated by planning for it, by having automated systems handle critical functions immediately after landing, and by giving the crew time to recover before attempting complex activities. But it's another factor that adds complexity and risk. The psychological experience of being on Mars is also difficult to predict. Mars is visibly alien. The sky is butterscotch-colored during the day due to dust suspended in the atmosphere. The sun appears about 2/3 the size it does from Earth. The landscape is rocky, barren, and utterly lifeless. There are no plants, no animals, no water, no familiar sounds except those made by equipment. The horizon is closer than on Earth because Mars is smaller. The day is slightly longer than an Earth day, about 24 hours and 37 minutes, which can disrupt circadian rhythms over time. The emotional impact of living in such an alien environment for a year or more is unknown. Some crew members might find it exhilarating. Others might find it oppressive. Analog environments on Earth, like Antarctic stations or deserts, provide some comparison, but Mars would be more extreme. The crew would need psychological resilience and strong group cohesion to maintain morale. Providing recreational activities, communication with Earth despite the delay, and a sense of purpose through meaningful work would all be important for psychological health. Mission planning also has to account for contingencies that have never occurred but could. What if a crew member dies during the mission? Death could result from accident, medical emergency, or equipment failure. The body would need to be handled respectfully while preserving limited storage space. The psychological impact on the remaining crew would be significant. The mission would need to continue with reduced crew, which might affect ability to complete objectives or handle further emergencies. What if the return spacecraft is damaged and cannot make the return journey? Does the crew attempt repairs, knowing they might be sacrificing themselves if repairs fail? Do they remain on Mars and hope a rescue mission can be mounted, which would take years to arrive? These are grim scenarios, but mission planners need protocols for them. The crew needs to know before launch what the plan is if things go catastrophically wrong. Having those plans doesn't make the scenarios less tragic, but it provides a framework for decision-making under extreme stress. The economic sustainability of Mars exploration beyond the first mission is also uncertain. The first mission would be driven by exploration and prestige. What motivates the second mission? The 10th? Space exploration historically has relied on a combination of government funding motivated by scientific advancement, national pride, and geopolitical competition. Private funding has recently entered space activities motivated by commercial opportunities in communications, Earth observation, and potentially space tourism. Mars doesn't offer obvious commercial opportunities. There's no resource on Mars that's valuable enough to justify the cost of bringing it back to Earth. Tourism to Mars is theoretically possible but would be extraordinarily expensive and dangerous for decades at least. Scientific research is valuable but doesn't generate revenue. Unless Mars exploration leads to permanent settlement that eventually becomes self-sustaining, which is a much more ambitious goal than initial missions, it's unclear what would fund sustained Mars exploration. This doesn't make the first missions impossible, but it makes long-term Mars programs uncertain. There's a philosophical question underlying all of this. Why go to Mars at all? The reasons are primarily intangible. Scientific knowledge, particularly about whether life ever existed on Mars and whether it still exists in subsurface environments. Technological advancement driven by solving difficult problems. Inspiration for future generations. Expanding humanity's presence beyond Earth as a form of long-term survival strategy. Testing our capability to explore and potentially settle other worlds. These are valid motivations, but they're not quantifiable in economic terms. They're values-based motivations. Different people and societies weight these values differently. Some see Mars exploration as a worthy goal that justifies the cost and risk. Others see it as a distraction from problems on Earth that need attention and resources. There's no objective way to resolve that disagreement. It's ultimately a collective choice about priorities. Assuming society decides Mars exploration is worth pursuing, the technical path forward is relatively clear, if not easy. Continue robotic exploration to better understand Mars's environment and resources. Develop and test technologies needed for crewed missions, including advanced life support, in-situ resource utilization, large-scale Mars landing systems, and better propulsion. Conduct long-duration missions on the ISS or future space stations to better understand human health in space beyond 6 months. Build and test components of the Mars spacecraft in Earth orbit. Send cargo missions to Mars to preposition supplies and test systems under real Mars conditions. Only after all these steps are complete and successful would it be reasonable to commit a crew to launch. This process takes decades and requires sustained funding and political will. Several space agencies and private entities have announced Mars plans with target dates in the 2030s or 2040s. Those dates are plausible if development proceeds without major delays or funding gaps, but they're ambitious. One of the subtle difficulties is that Mars missions require many different technologies and capabilities to mature simultaneously. If life support systems are ready but landing systems aren't, you can't launch. If propulsion is ready but in-situ resource utilization isn't proven, you might not have enough confidence to commit crew. Every component needs to reach flight readiness at roughly the same time, which requires careful coordination across many organizations and programs. Delays in one area delay the entire mission. This coordination challenge is as significant as any individual technical challenge. Large complex programs have a tendency to encounter unexpected delays. Keeping a Mars program on schedule for 10 to 20 years would be a management achievement as much as a technical one. There's also the matter of unintended consequences and unknown unknowns. Every space mission has taught us things we didn't know. Apollo taught us about lunar dust problems that weren't anticipated. The ISS taught us about vision problems from intracranial pressure changes that weren't predicted. A Mars mission will certainly encounter surprises. Some will be manageable. Some might be serious. The question is whether the mission design has enough margins, enough redundancy, enough crew capability to handle surprises. Designing for the unknown is difficult because by definition you don't know what you're designing for. You build in general resilience, multiple layers of backup, cross-training so multiple crew members can handle critical tasks, and supplies beyond minimum requirements. You plan for things to go wrong in ways you haven't anticipated. That's expensive in mass and complexity, but necessary given the inability to abort or receive help. Let's return to the original assumption. The Moon is 384,000 kilometers away, and we reached it with 1960s technology. Mars is 143 times farther, and we have 50 years of additional advancement. So Mars should be achievable. The error in that reasoning is treating distance as the primary variable. Distance matters, but duration matters more. The Apollo missions lasted 8 days. A Mars mission lasts 2 to 3 years. The ratio isn't 143 to 1. It's about 100 to 1 in duration. And duration is what determines life support mass, cumulative radiation exposure, system reliability requirements, crew psychology, and the irreversibility of the mission. The Moon missions could abort. Mars missions cannot. The Moon is 3 days from Earth. Mars is 3 to 9 months from Earth depending on orbital positions. Help can reach the Moon in days. Help cannot reach Mars in any useful time frame. The difference isn't quantitative. It's categorical. Mars missions are not harder lunar missions. They're an entirely different category of endeavor. The second assumption was that we keep astronauts alive on the ISS for months, so we know how to do long-duration life support. That's true for 6-month missions with resupply every few months and evacuation available within hours. Mars missions remove resupply and evacuation entirely. The ISS is a testbed where systems are refined over time. A Mars spacecraft must work correctly from departure. The ISS has continuous communication with ground control providing support. Mars missions have delayed communication and must operate autonomously. The lessons from the ISS are valuable, but they don't prove we can do a Mars mission. They prove we can maintain life support for 6 months with significant external support. Mars requires maintaining life support for 3 years with no external support. That's a much harder problem, and it compounds with all the other challenges. The third assumption was that Mars is relatively close on a cosmic scale, implying the problem is achievable. Mars is close compared to other stars or even outer planets. But human spaceflight isn't about cosmic scales. It's about human scales. Humans need air every few minutes, water every few days, food every few weeks. Humans experience psychological stress from isolation. Human tissue is damaged by radiation. Humans are fragile biological systems that evolved in a very specific environment, and every other environment requires technology to keep us alive. The scale that matters isn't the cosmic scale. It's the human biological scale. On that scale, Mars is devastatingly far because the duration of the journey exceeds our current ability to maintain human health and safety without support from Earth. So why is it so hard to reach Mars? Because reaching Mars with humans requires keeping complex biological systems alive in a hostile environment for years without resupply, without evacuation options, without the ability to abort, and with minimal communication support. It requires building spacecraft that function reliably for years in radiation and vacuum. It requires launching hundreds of tons of equipment and consumables from Earth. It requires landing tens of tons on Mars with precision. It requires psychological resilience from the crew beyond anything currently tested. It requires solving medical problems with limited equipment. It requires sustained funding over decades. It requires technologies that aren't yet mature. And it requires accepting risks that are higher than any previous crewed missions. None of these challenges are individually insurmountable. But all of them together create a problem space that exceeds our current capabilities. We will likely go to Mars eventually. The technologies are being developed. The motivations exist. The question isn't whether it's possible in principle but when it becomes feasible in practice. And feasibility isn't just about technology. It's about acceptable risk, sustained commitment, and collective will. Mars missions will happen when the technologies are mature enough that the risks are acceptable to the people making the decisions and to the crews taking those risks. That point hasn't been reached yet. We're working toward it. Progress is being made. But the original assumption that Mars should be straightforward because we went to the Moon misunderstands what makes Mars difficult. It's not the distance. It's the duration, the isolation, the irreversibility, and the compounding of every challenge over years. Understanding that distinction is essential to understanding why Mars missions haven't happened yet, and what needs to change before they do. If this breakdown helped clarify the actual constraints beyond simple distance, and you'd like to see more explanations that work through assumptions in this way, the subscribe button is there for exactly that purpose. This channel focuses on these kinds of careful examinations of space topics, where the goal is understanding rather than inspiration. Thanks for watching.